introduction. Thank you for the invitation to begin with. I'm honored to speak at such an event. Of course, I would be happy to do it in person, but oh well, things are different these days. But every crisis is also an opportunity, so we have possibility for many people to connect from all over the world and listen to the conference where we could not attend before, because now most of them are online. So let's use the best of what we can. Do you see my screen okay? It's now in the full screen mode. And if yes, then I can start. Great. Okay, so sterile neutrinos. What are they? Where do they come from? And what are they good for? Usually when we start to speak about any physical model or new physical concept, you ask the questions, why, what, and how does it work? So why do we need new particles, sterile neutrinos or whatever? What are these particles? And how do they help to solve us any problem? Because you don't find a solution until you have a problem. So why do we have these particles? Because there are observed phenomena that we do not find their resolution within otherwise successful theory of elementary particles which exist today. We don't know what these particles are, and what I'm presenting to you is one of the hypotheses on the scientific market, so to say. It's well accepted, it's well developed, but this is one of the hypotheses, and they are all at equal footing right now. They are all in the stage of testing. So you should keep this, please bear this in mind through the talk. And how this particle solves the problems and what are the problems, that's the subject of my talk today. So very briefly, what is particle physics? Once upon a time, about a century ago, the particle physics was very simple. People knew that atoms exist, people discovered electron, proton, they knew about electromagnetic interactions, and it seemed that all the ingredients are there. Electrons are attracted to protons and form atoms. However, there were several puzzles or unanswered questions, like why electrons sit on stable orbits, why some of the nuclei are radioactive and emit alpha particles, why other nuclei are radioactive and emit beta particles. And in an attempt to build a complete theory of atomic physics, people went further, discovered extra particles, and it took them literally a century, from an electron in 1897 to the Higgs boson in 2012, to build a consistent theory of atoms. Because until the Higgs was discovered, the beta decay was not really explained. We all thought we knew the answer, but physical model becomes accepted only when its predictions are confirmed. And a very far-fetched prediction of a beta radioactivity of nuclei is the existence of the Higgs boson, as surprising as it may sound. And therefore, until 2012, strictly speaking, we did not have a fully working theory of radioactivity. Trying to be paradoxical here, but that's actually true. Now, standard model of particle physics. That's how we call the theory of elementary particles today. To give you an idea how much has been done through the century plus when we were building the theory, I'll show you here a book known as PDG, or Particle Data Group Book, which collects every year or every few years everything which is known about all elementary particles, properties about their masses, lifetimes, everything which has been measured. And what you see here is the evolution of these books published in a very thin paper from 1950s or so at the bottom to recent years. So these are several thousand pages which describe everything which is known about these 17 particles. And that pile of different editions of the same book shows you how much have happened in the particle physics within a century. And understanding that people here come from with different backgrounds, I'll probably give you a very, very brief, really not trying to be pedagogical or exact, some very brief overview of what you see on this table. So these 12 particles are called matter. These 4 types of particles, which are on the right, are called interactions or mediators of interactions, because since Maxwell, we believe, and we never saw a counterexample, that every interaction is mediated by a messenger sent from particle A to particle B. And there is also a Higgs boson, which is strictly speaking both matter and interaction. And you see that picture have changed drastically from this simplistic view of the beginning of the 20th century. So for example, there is no proton here anymore. Proton is a collection of quarks, which are kept together by these gluons. What is here? These 2 quarks plus electron plus electromagnetic radiation is everything which tells you about atomic physics and chemistry. You build protons and neutrons out of these 2 quarks, you add electrons, you let them interact, and the whole rich phenomena with enormous amount of consequences and applications is there. Your nuclear physics is even simpler. Everything from atomic bomb to a nuclear power plant sits in just these few quarks interacting strongly. And also the alpha radiation of nuclei sits here. A beta decay, as I said, it's a very universal process. It's called weak interaction because of the weakness of its strengths, but it's very important because every quark, every electron, neutrino, is weakly interacting. And also a Higgs boson is a big part of weak interaction. So almost every particle here is in some way involved in explaining what beta decay is. Finally, to tell you why I say that standard model of particle physics is very successful, I show you this plot. That's a real experimental plot, which is known as a stairway to heaven because of its shape. Now, what you see here is the following. On the x-axis, there are various processes observed at Large Hadron Collider. Large Hadron Collider is several experiments, and they do thousands of measurements, if not millions, of different measurements. And these are some of the selected measurements. And on the y-axis, you see roughly how rare a particular event is. So if somewhere at the top, you see the process which happen essentially in every collision, somewhere here you see processes that happens once per trillion collisions, and even less. So there are 14 orders of magnitude between this process and this process. So this process have been observed in dozens through many years of operation of Large Hadron Collider. And that just shows you, that explains to you what goes into this thousands of pages of those books of particle data group. But that's not it. Color-coded are measurements done at different stages of LHC operations, but there is also great rectangles, which are theoretical predictions. And the beauty of this plot is in the fact that you do not see theoretical predictions behind the color plots. I mean, they are on top of each other, which means that your prediction is confirmed by your measurement. And that's impressive, given that this is a century-long model and that the people who started it are that long ago, and given that Large Hadron Collider is extremely complicated machine, when there is not a single person who understands everything about it. And all this enormous complexity is brought together and it works. And it's completely a miracle. Scientific miracle, but still a miracle. And I really hope you appreciate it. And that's why when we say standard model of particle physics, when we call this model the standard model, we actually mean it. It's so well working that it's definitely a good theory of nature. What we observe, we describe very precisely. However, physicists would not be real physicists if they would not try to challenge their own thinking. Therefore, at every stage of operation of Large Hadron Collider or any previous experiment, people search for unexpected, unknown. And this is just some slide which indicates for you that there are enormous amount of signals in our detectors, which standard model particles would not produce. And we search for them. And we search for them, and we do not find them. And what does it mean we do not find them? When we do not find them, we exclude theories and hypotheses that have predicted some such signatures. And what you see here in this beautiful, funny slide is a symmetry of old ideas. Now, what is old? These are ideas which were there before Large Hadron Collider has started. There were certain expectations, certain anticipations of the community. And there was a big gap between previous experiment, Tevatron, and Large Hadron Collider. And during this gap, people were trying to guess and suggest what can be probed at Large Hadron Collider. And they came up with hundreds of ideas, very brilliant, very well developed. It's just 2 generations of scientists sits behind these ideas. And all of them did not find their confirmation. So it's a very remarkable graveyard. It shows you the beauty of science. Science is falsifiable. You may very much like your idea. You come, you make a prediction, you test the prediction, and it's gone. And you start to do something else. Yes, the idea is not mine. That's beautiful. I agree. Now, given all this, so well working standard model, no observed signals which would not be part of it. Is there anything else to search, or should we just shut down Large Hadron Collider, save a lot on the electricity bill which it generates, and do something else? Condensed matter physics, new materials. Now, the thing is that there are observed phenomena beyond standard model, beyond the reach of the LED of Large Hadron Collider, cannot be probed there, and not in the standard model. What are they? Again, we have to go back to beta decay problem, mid-1920s. People are discussing the fact that carbon can become nitrogen and emit a beta particle, which is electron, known by that time. They predict, based on the energy conservation, that all electrons should have roughly the same energy. So number of electrons is a function of energy, and this energy is just a deficit of mass between the 2 nuclei. They predict this, and they observe this. And seemingly, all you put into your consideration is the fact that energy is conserved. So they are so desperate that they start to suspect that energy is not conserved in quantum processes. This is a dawn of quantum mechanics. People are experimenting with all sorts of challenging of the conventional thinking. In the situation that desperate, Pauli proposes that actually what happens here, it's not a carbon becomes nitrogen electron, but carbon becomes nitrogen, electron, and new particle, which has become known as neutrino. And because the energy is conserved, but it's distributed between these 2 particles in some probabilistic matter, and so electron never gets the whole energy; it gets some fraction of it. This fraction depends on like angle between the particles essentially, and that's what explains this spectrum. Very good idea, but this particle is neutral. And at that time, the only kind of interaction is electromagnetic interaction. And Pauli says, oh, if particle is neutral, it cannot be detected. So I have a famous quote, I have done a terrible thing and I invented a particle that cannot be detected. And there is no doubt that Wolfgang Pauli is a very smart man, very unorthodox thinker. And that's one of his great predictions, which was confirmed only 30 years later. However, in this aspect, he's bloody wrong, because there are 3 Nobel Prizes given for neutrino discovery, related to neutrino discoveries. And of course, there are infinitely many works about working with neutrinos. So even great minds may be wrong sometimes. Neutrinos, they're neutral, they're extremely light, they are very, very weakly interacting. As you know, like when photons are created inside the sun, it takes for them millions of years to come from center to the surface and then come to us. Neutrinos just go through. Neutrinos is the second. I'll answer the question later. Neutrinos are the second most abundant particle in the universe after photons. Neutrinos are produced by all sorts of things, by stars, by supernovas, by our reactors, by our accelerators, by all kinds of things. There is a lot of interesting and fun stuff about neutrinos. I'm sure you heard some of it. Now, what I want to talk about is a problem with neutrinos. What's the problem with a particle? Well, the problem number one is that this is not a particle. Strictly speaking, it's half of a particle. What do I mean? All the particles which are fermions, they have spins. They have two orientation of spins, up and down, or along the direction of a movement and opposite. Every quark, electron, muon, tau, every other fermion has two chiralities, or two polarizations, or two helicities, whatever you call it, the way you like. The idea is clear. Neutrinos only have one. Neutrinos are always left chiral, and antineutrinos are always right chiral. Why that's a problem? It's not a problem per se, but it means automatically that neutrinos do not have mass, because mass is something which takes one polarization, so vector pointing this direction, and couples it with another polarization, so left to right. Mass is left-right symmetric object. It cannot be constructed out of left only. That's why all fermions, all particles with spin 1/2 have mass, and neutrinos should be massless because there is nothing to make mass of. Good. How do we know that they're half of the particles? That's another great story, which goes back to mid-20th century. That's a famous experiment by Wu et al., who was considering the same beta decay. It's an extremely powerful tool which gave us so much knowledge about physics. And she puts some nuclei into the magnetic field to align their spins. She looks like electrons fly out in which direction. And then she notices that this distribution is up-down asymmetric in such a way that if you would put a mirror to your experiment, you would see a mirror image. So essentially what the mirror is called in this language parity, which is just flipping with the direction of all the coordinates. So you observe this, and parity would map it to this, and you don't observe it. So you see the world, which is completely left-right asymmetric. To put it in perspective, you know that there are some things in the living nature which are asymmetric. Some of the snails or shells have only one winding. Some of them can be left and right, some of them can be on the left, some of them can be on the right. Here you are in a situation when a neutrino wakes up in the morning, looks in the mirror, and doesn't see itself. Imagine that happens to you, should be shocked. So is neutrino. Because a mirror maps left to right, that's kind of left-right reflection, and there is no right neutrino. To put it differently, for a normal particle, if there is a decay involving two particles, then you may exchange left polarization with right polarization, or you may exchange particle with antiparticle. But for neutrinos, if this process exists, this process never observed, this process never observed, and only the process where you simultaneously change left and right and particle with antiparticle is possible. So essentially, when particle looks in the mirror, when neutrino actually looks in the mirror, it sees its own antiparticle, antineutrino. I don't know the analogy with us humans, so sorry. But imagine that that's a strange story. But even this is a well-known fact, goes back to 50s, and this is known as parity violation in weak interactions. So our world at intrinsic level, our elementary particle physics world, is not left-right symmetric. Good. People accepted this fact. However, later people understood that that's not the whole trouble with neutrino. Neutrinos come in three types because there are so-called three generations of particles. There are electrons, muons, and taus, and there are electron neutrinos, muon neutrino, and tau neutrino. In the sun, as a consequence of nuclear reactions, neutrinos are produced only of one type, of electron type. However, when people measure the flux of neutrinos coming from sun to the Earth, and this was done in the 60s, they see about 1/3 of the predicted number. Moreover, that was known as the solar neutrino problem, and people spent decades trying to adjust the model of thermonuclear reactions in the sun to account for this number. They failed. The model of the sun was working properly. Everything else worked, but it predicted wrong number of neutrinos. Then people discovered that actually what comes is the number of neutrinos which comes is correct, but neutrinos come of a different kind. They are not produced in the sun, yet they appear. What does it mean? This phenomenon is known as neutrino oscillations, and the latest neutrino Nobel Prize was given for this. What is this kind of oscillations? First of all, apart from neutrinos, this transition between types is forbidden in the standard model. Every other process obeys this selection rule, if you wish. And there are numerous experiments which try to test deviation from this in non-neutrino sector. They're all negative. And all of a sudden, neutrino do it with probability equal to 1. What the hell? Now, what does it mean neutrinos are oscillating? More or less. Philosophically speaking, you can define particle in 2 ways. Particle is something, it's a packet of energy which propagates through the space with a given dispersion relation. You know that there is a particle-wave duality and particles and wave, and you can think about propagating particle as a wave packet. Good. On the other hand, so particle is something that propagates with given mass and relation and velocity. On the other hand, particle is something that interacts in a given way. And very often, more often than not, these 2 definitions are completely the same. If I take an electron and I tell you electron is something that interacts electrically with such and such strengths and propagates through space with such mass, it's the same electron. If I take a photon, it's the same photon. If I take a proton, it's the same proton, whether I define it through interaction or through propagation. For neutrino, this is not the case. The particles that interact, known as electron neutrino, muon neutrino, and tau neutrino, is a quantum superposition of 3, or at least 3 states. Each of them propagate with given velocity, but they are not the same. One is a mixture of another. So when electron neutrino is created in a certain process, you create some quantum superposition of 3 states, which then propagate each with their own velocity. And so there is a phase shift between them. And so at the end of the day, if you look at this wave packet later and again try to see how it works, and I encourage you to look at this YouTube video, which does a beautiful animation of the story and explanation. You see that the probability to detect neutrino of a given type changes in space or in time. And you can do the measurements by just looking at the beam of neutrinos going from a reactor somewhere and putting detectors along the way, and you see that indeed number changes in a certain way. This way doesn't look like a sinus to you because you can change it to different types, so it's a very complicated process actually at the end of the day. But your prediction does work, and works very well. And we really see the oscillation pattern in space, in time. We observe it with high confidence. And this is something which standard model does not explain. Neither the mass nor the proper possibility of oscillations. I should stress that oscillations imply mass, but not the other way around. That's why sometimes this phenomenon is just called neutrino oscillations, and mass follows from it. And this phenomenon is known as beyond the standard model phenomenon, this ability to change type in flight. And something should explain, some new particles should be there to explain why this happens. Now, it's a good question about if I found something that contradicts the standard model, doesn't mean the standard model is ruled out. No, it does not. Because look at this in the following. There is a core of a standard model with all this stairway to heaven, all this PDG measurements, thousands of measurements. They work. Now we understand that actually the actual model is bigger and its core is the same standard model. Now we are trying to see what's on the outskirts. So neutrino opens for you a passage an extra room. Like imagine that you are playing a computer game and you are going through the labyrinth whose map is not known to you. And you have some map, and this map is true map. But you are not aware about the hidden door on the left or what's happening beyond the corner. And what you do, you move there, you open new door, your card become, your map of the labyrinth or of the level, game level becomes bigger, wider. But it doesn't mean that it's that the previous map isn't valid anymore, right? That's what's happening. We suddenly recognize that neutrinos behave differently. Now we need to explain why they do so, and we also need to explain why this does not invalidate other observations of the standard model, that other particles don't do it. Because it's very easy to invent the explanation which will ruin other observations as well. It will fix this one, but ruin another one, and you're not allowed to do this. You are only allowed to fix the standard model, that's why we call it extend, not change, but extend, without really breaking it. Let me show you how it works. And if I didn't answer your question satisfactorily, you are welcome to ask more questions. So finally, sterile neutrinos, half an hour into the talk. Looking at this picture, it's kind of obvious what we need to do. You ask, what about the second half of neutrinos? Can there be right chiral neutrinos? Here they are. Now, it turns out that these particles are very special particles. A right chiral component of electron is no different from a left chiral component of electron. But for neutrinos, owing to them being neutral particles and some other subtle properties of the standard model of this thousands of pages of particle data group, these particles not only have different chirality, which will be okay, but they also may have their own mass, known as Majorana mass. We are not allowed to go into details given time, but these particles may have their own mass, not given by the Higgs. So all other particles receive their mass through Higgs. These particles bring their mass with themselves. Because they carry no charge, they are sterile neutrinos. They are not charged with respect to weak interactions, electromagnetic interactions, or strong interactions. So they are sterile particles. Massive, truly neutral. Even neutrinos are not truly neutral. They experience weak interactions. Here, we are finally finding a truly neutral particles. Now, how do they give mass to neutrinos? They give mass to neutrinos through something called Seesaw mechanism. So if these are my known left chiral or left-handed neutrinos, and these are my new right chiral heavy neutrinos, which came with their own mass, then the mass that we observe is the mass of the heavy in the denominator times some interaction of two kinds. This is small if this is big. That's why it's called seesaw. And let me explain to you how mass works. So there is a massless state. Think about the electron neutrino. It's massless, it flies. Then there's a probability for it to become a right chiral or sterile neutrino. This probability is small, but it's not zero. This one is massive. Now, this propagates with the speed of light, this propagates with a slower speed. Now, there is the same probability to go back into this. Now, look from the process from beginning to the end. It's like electron neutrino flew through space, but some of the time it was moving slower than speed of light, if you wish. Which essentially means that there is some small mass. Why it is small? Because this probability is small. So this mass is large, but this probability is small. And multiplication of these two numbers gives a small mass to neutrino. Now this is how low probability and high mass gives a small mass to our observed neutrinos. How do oscillations work? Well, that's another story. It starts with the same left chiral electron neutrino. There is a probability for it to become right-handed neutrino. Now, in the previous case, there was a probability for it to go back into itself. But it turns out, and this is part of our model, mathematically well formulated, but omitted here. But there is also probability for it to become, for this guy, to become a different kind of neutrino. So they do not really belong to one type. These neutrinos mix the types. And so in this way, oscillations happen. So oscillation of electron neutrino to muon neutrino or to tau neutrino for that matter is secretly active, sterile active process. Again, with all the necessary details which are beyond the scope of this talk. Okay, so I came to you, I brought you this new shiny idea and I tell you, buy it. And I really mean buy it, because tomorrow you will decide what to do a master's or a PhD on, and you will have to choose a model. And I'm trying to sell you a model. And you may spend 10 years working on it, and then it will end up in the symmetry of old models, which I showed you at the beginning. So you really should be much more careful than when you're buying a jar, because the price you pay is much higher. It's your career, it's your life. So don't buy, first try. What would be our best question to ask here? Can these neutrinos explain all the observed neutrino masses and oscillations, of which there are many, because we measure 1, 2, 3, 4, 5, 6 parameters? Yes, we can. Sterile neutrinos allow us to explain all the neutrino measurements. Good. How many sterile neutrinos should there be? 3, good number. Actually, even 2 is allowed. But of course, 3 looks nicer on this plot. Do we know their mass? Yeah, I told you that they come from the same mass. The answer is no, we don't know their mass. Their mass can be very small, down to milli-electron volts, or can be extremely large, just to guide you through, and different kinds of models predict for you different sterile neutrinos. So this is somewhere range of electron, more or less here is the range of a proton, Higgs. This is not up to scale, so it's very roughly. Or super heavy particles, which we never produce because our accelerators don't reach there. So from lightest particles to heaviest particles, this can be mass of sterile neutrino. Unfortunately, we don't know. Now, that's probably the main question. So once I told you that they explain what they are designed to explain, the next question is, are they used for something else? Can we kill 2 birds with 1 stone, or many birds with 1 stone? Yes. Let's see how this works, because that's the most interesting part. Now, along with neutrino, there are other beyond the standard model problems related to the cosmic frontier. Yakov Zeldovich, who considered one of the fathers of modern cosmology, Soviet physicist in the mid-20th century, once said, "The universe is a poor man's accelerator. Experiments don't need to be funded, and all you have to do is collect experimental data and interpret them properly." Unfortunately, the experiment has only been done once. What does it mean? It means the following. Cosmology is a very brave and very crazy, if you wish, attempt to extrapolate things that we measured here on Earth to the whole universe. No more, no less. The laws of gravitation applied to the universe imply the Hubble law and the fact the universe expands. The thermodynamics, laws of thermodynamics, the one you know, first and second law of thermodynamics, tell us that this lead to the hot Big Bang theory, where in the past the universe was hotter and denser. The atomic physics and its laws tell us that atoms ionize or recombine, depending which way you move in time, and explain to you the radical radiation of the cosmic microwave background. Nuclear physics, put into the hot, dense early universe, leads to the prediction of the abundances of primordial elements, hydrogen and helium. Finally, physics which is done by the Alice, one of the LHC experiments, would explain something which happened in the universe beyond our observable frontier, and so on. So essentially, all the physics that we know is applied to the universe. And altogether, it gives us this picture, which you probably saw many times in different disguises, And this picture is not a cartoon, it's not an illustration. You can really put here details, compute the numbers, match every picture with some observables. This is a very precise fundamental science. Now, what's important about this? That everything here is not an experiment, not an observation. It's many, many observations. And each experiment produces its own contour of confidence. It tells you that certain cosmological parameters should lie in this blue area or in this light blue area with smaller probability. And then another experiment comes and says the same cosmological parameters should lie in this green area or with lower probability in this greenish area. And the fact that they overlap is amazing. But then there is a third experiment comes, and you understand that chance for the three lines to intersect in one point is really slow if it's by chance. And it also happens here. And so altogether, they produce a very small range of probable values of parameters. And another measurements of another parameters reconstruct this picture. And that's a beauty and power of modern cosmology. As a result, we have this cosmic pi, which I'm sure you saw hundreds of times. And all the numbers here are known as percent precision. And it's a combination of dozens of experiments. Now, what's important here? Here comes another beyond standard model problem. There is this beautiful picture of cosmology, particle physics applied to the universe. Very nice measurements, everything consistent. Here comes a story. Very shortly, in 1930, Dirac, trying to build the quantum theory of electron, came to the conclusion that along with electrons, there should exist another particle called positron, which is antiparticle, example of antimatter of electron. Now, it's a particle with the same mass and lifetime and opposite electric or other possible charges. And when the two particles meet, they annihilate. You probably know about this. Now, you may or may not know that the universe is devoid of primordial antimatter, which means that although today physics is particle-antiparticle symmetric, people have just constructed a certain anti-hydrogen and behaves like hydrogen, has the same atomic transitions. There is no antiparticles in the outer space, no anti-helium. There's a lot of helium and no anti-helium, 1 per million probably. What does it mean? That's actually a very interesting fact. When the universe was hot and dense, there were many particles and many antiparticles, so quantum soup boiling. And then all those particles and antiparticles started to annihilate. And as they did, it turned out there was a small disbalance, 1 per billion. So when all the particles and antiparticles annihilated, something remained. Not only the relic radiation, but also some particles. And we, our planet, our sun, all other stars are made of this leftover, 1 per billion leftover. So tiny discrepancy between the amount of matter and antimatter in the universe, in the early universe, led to this. In the standard model, this would be impossible. In the standard model, this number would not be 1 per billion, but 1 per 10 to the minus 12 and 20 or so. And you would not see the universe as we see it today. Now, can sterile neutrinos help us to create matter-antimatter asymmetry in the universe? Oh, yes. How does it work? Here, what comes to your help is the fact that there are two sterile neutrinos. So, in the early universe, the probability of the process, our neutrino becomes sterile neutrino, is actually supplemented by the process that these two can oscillate into each other. Sterile neutrino number 1 can oscillate into sterile neutrino number 2. It's similar to neutrino oscillation, but in the sterile sector. And then it oscillates back to neutrino. So far, nothing interesting. Things become interesting when you understand that the probability of this process is not the same as the probability of the same process in the antiparticle. So antineutrino, anti-sterile neutrino, and so on. So these two processes have different probabilities. So through these oscillations, you slowly accumulate particle-antiparticle difference. Through a complicated process known as Fallerons, this gets converted essentially to us. So matter-antimatter symmetry of the universe is a result again of oscillations, this time not of neutrinos, but of sterile neutrinos. And that's not the only possibility. I just put it there for simplicity. There are 50 models of this kind. And that explains this wide range of masses. In different masses, different mechanisms work. But overall, that's an idea. So the same sterile neutrinos, which explain neutrino oscillations, can also generate observable matter-antimatter symmetry of the universe, which is beautiful. Let's come to another problem. Dark matter. You all heard about this. We observe some stars. We know that stars are more or less like sun, give or take factor of few. By their luminosity, we can deduce their mass. We can compute how they should rotate in a galaxy. Their rotation velocity should reach the maximum and fall. Instead, it behaves in this form. While the galaxy is more or less luminous, that's this. And then there is it seems like a galaxy is embedded to the huge dark halo. We do some gravitational lensing, kind of direct deduction of amount of matter in the universe. This is the same. There is this famous picture, which again you might have known as bullet cluster. It's a event when two clusters of galaxies. So what's cluster of galaxy? It's like galaxy is a trillion of stars. Cluster of galaxies is a trillion of galaxies moving together. So it's the biggest object in the universe. They just happen to move through each other. And as they move through each other, stars do not interact. The gas which fills these clusters does interact and gets pulled behind. So you see that there is matter which goes through without interaction. And there is matter which we know about, atoms, ions, electrons, which gets pulled behind by when this smaller cluster came from left to right to the big cluster. Now, and that's dark matter. Again, dark matter is not a phenomenon. It's dozens of different observations, not even observations of different groups, but observations of different nature. And the fact they all consistently point to the same picture is very remarkable. Now, what do we know about dark matter? That it doesn't emit any detectable light or other radiation, and that it's not made of non-elementary particles. None of those particles, even not neutrinos, can be part of the standard model, can be dark matter. So, whatever dark matter is, it's not this. It's some unknown animal in this animal analogy. Strictly speaking, it doesn't even have to be an animal. It can be many animals. We don't know. Now, coming back to our story, can sterile neutrinos help to explain dark matter of the universe? Oh yes. Essentially, the same Seesaw mechanism which makes our neutrinos lighter than sterile neutrinos also tells us that the sterile neutrinos are interacting by the same token weaker than usual neutrinos. And that's why they are kind of not interacting with anybody, not even with light, not with other particles, and they just sit there. They are produced in the hot and early universe, and then they just stay there by themselves, lonely and bored. And yes, there is a whole physics about sterile neutrino dark matter. I spent years working on it as well. But it works. And what's even more interesting, there are three major beyond the standard model problems: neutrino masses, oscillations, matter-antimatter symmetry of the universe, and dark matter. They do not find their resolution within the standard model of particle physics plus cosmology. But sterile neutrinos, three of them, are enough to explain all of them. And that's what makes the model so nice and beautiful and interesting. Now, you should ask, if it's so well, is it some new idea which appeared yesterday? Why we don't read about this in every newspaper? No, it's old idea. The idea that sterile neutrinos can explain neutrino oscillations is half-century old. Then people understood that the same particles can explain matter-antimatter asymmetry. Within 10 years, they understood that the same particles can be dark matter, some combination of those. And only in 2000s, people understood that sterile neutrinos can explain all of this within one framework. And that's what made this model so interesting. Plus the fact that none of these particles would show up at the LHC in any visible way so far. And therefore, the fact that we do not observe any deviations from standard model at the LHC is well consistent with this hypothesis. I mean, it's a negative prediction, but still. Now, can sterile neutrinos still be discovered? The answer is yes. At Large Hadron Collider and its successor, whatever it will be, maybe Future Circular Collider of 100 kilometers long, maybe something else. At many experiments like SHIP or Phaser, I can speak about this for a long time, but I need to go to your questions probably. They can be discovered. You may ask when? Anytime. There are experiments which are searching for them right now, and tomorrow they may report a result. There are experiments which will start running a year from now, 5 years from now, 10 years from now. In the data of Large Hadron Colliders, there may be signatures of sterile neutrinos of certain masses. It's wide open and interesting field. Now, I don't know whether I was able to use a stainless jug, but hopefully I did. And so let me wrap up the story. Standard models we know today, plus the puzzle of neutrino oscillations, plus the puzzle of the cosmic pi, may very well be pointing to a new model, which is sometimes called neutrino minimal standard model, which contains only 3 additional particles. This is the most minimalistic, the most economic extension of the standard model that exists today, which does not make it correct, but it makes it interesting and testable. So, thank you for your attention, and I will be happy to start answering your questions.
Hi, Oleg. Thank you so much for that. That was so interesting. Yes, if you could answer some of the questions, I think we've got quite a few. That would be brilliant.
Okay, so I'll try to go from top down and answer them. The first question is about the stairway to heaven. Now, the question about the stairway. So, let me grab that there. Yes. So, what you ask now, there is no direct relation between collision energy and how rare can the particles be produced. Answering your question. So the question is that 8 CV are more rare than 7 CV. It's not the energy which gives this, but rather this number, Fb to the power of -1. It's called the luminosity. Luminosity is the following. It's how often your particles interact. Very roughly, at the Large Hadron Collider, there is a bunch of particles, 10 to the 11 of them, moving in some small region of space, but still very diluted. And there is another bunch of particles. Both beams are focused. In principle, they can even go through each other without much interaction. However, you, as accelerator physicist, try to bring them to such a crash course that as many as possible of them interact. Number of potential interactions is called luminosity. And the luminosity here is 4 femtobarns. So if you multiply this number by this number, this is femtobarn, and this is picobarn. So there is a factor of 1,000 in between them. You should get roughly the number of events which were produced. Okay, so here it's factor of 5 difference. So here you should expect to see factor of 5 more rare events. Here it's another factor of 1/2 to 2 difference. So you should see even more rare events. Okay, that's how it works. Again, I'm not going into details because I don't have time, but that's more or less why this happens. Now, next question about neutrinos. Does it mean the high energy neutrinos travel very fast and low energy neutrinos travel very slow? Well, in a sense, yes. I mean, when you say, the particle has mass, so its speed is essentially different from speed of light by mass divided by energy. So TeV neutrino is traveling closer to the speed of light than MeV neutrino. But there is no such thing as particles traveling very slow. In all possible neutrino experiments, neutrinos travel, our neutrinos travel almost with the speed of light. For sterile neutrino situation may be different. You can produce a relativistic or non-relativistic, and that's very much dependent on what is discussed. On the details of a model. Now, somebody asked me about the difference between scalar and gauge boson. Now, gauge boson is a particle which mediates interaction, and by its Lorentz nature, it's a vector. So it has 4 polarizations which are related in a certain way. Scalar is a scalar; it has 0 polarization. So it's one internal degree of freedom. Okay, it's the scalar and the vector are different tensors. Probably that's the word which makes sense. And you probably want to ask in which sense Higgs is a mediator of interaction. Well, Higgs does not mediate any interaction, although in principle you can see the process which looks very much like a particle. One particle emits a Higgs boson, another particle catches a Higgs boson. In this sense, it is similar to the interaction, but there is no new type of interaction associated with the Higgs. It's still only weak, strong electromagnetic interactions. And so there are only photons, gluons, and double-ends and bosons. By the way, you are welcome to ask again if something which I said is not clear, okay? So don't. I will remove those which are done and we'll continue. Now, the question is why the probability of oscillation between sterile neutrinos and antineutrinos is different. And by the way, the probability of oscillation between active neutrinos, electron to muon, and anti-electron to anti-muon may also be different. That's one of the unmeasured so far properties in neutrino physics, which is being measured right now. We don't know, it's a particle which is being experimented. This is measurement which is being done as we speak. So in a sense, we do shift the matter-antimatter problem into the sterile sector, but there is an important aspect here. In the early universe, it's so hot and so dense that even neutrinos are interacting with everything. Like you know, for example, that inside the supernova, neutrinos are trapped. They are not moving freely. Through the sun is not dense enough. Through sun, they can move. But through supernova, proton-neutron star, they cannot move freely. Early universe is even denser. So neutrinos are stuck there. And because of that, any difference between particles of antiparticles will be erased. Cannot go into details, just take my word for this. Sterile neutrinos, because of their super weak interactions, are not stuck there. They move freely through the early universe, even through that dense part of it. And because of that, whatever difference in particles and antiparticles they produce will stay. If you are curious, it's known as a Sakharov condition, one of the 3 conditions for successful matter-antimatter asymmetry of the universe generation. Now, before I continue, I should ask the question: can I continue slightly past 3, or we should end sharply?
Hi, you're more than welcome to keep going. If we've got quite a lot of questions, so
okay, then I'm comfortably answering them. Very good. I just didn't want to be interrupted in the middle. Okay, very good question. How can sterile neutrinos be detected? Yes, I'm like Pauli. I told you there is a particle which bears no interaction. How can it be detected? Very good question. Essentially, it gets detected in the following way. So let me find a diagram. Probably this one would be good. So look at this process, but now forget about this part. Well, first of all, you can create a beam of neutrinos. In this beam, with this probability, there will be a mixture of these neutrinos. There is a subtle difference which I completely skipped here between real particles and virtual particles. But it may be that in the beam of these neutrinos, there is some admixture of these neutrinos. And then, because they interact with ordinary neutrinos, and ordinary neutrinos interact with other particles in a beta decay-like process, this kind of mediated beta decay may happen. Does it happen often? Well, to give you an idea, if this particle has a mass of a proton, then it interacts trillion times weaker than usual neutrino. So, first of all, it's created about once per trillion of neutrinos, which sounds huge, but it's quite possible to generate that many neutrinos. And then, with equally small probability, it can decay through neutrinos. Okay, so essentially, one of the experiments which you can imagine, which is done, for example, I'm just rolling to the last slide. Bear with me for a second. Yeah, in this experiment, there are protons. They come from here. These protons from the SPS. I mean, from the SPS. They hit this target. They create all sorts of particles, which decay and produce many neutrinos. And then all this greenish and reddish stuff, it either stops all known particles or sweeps them away. So after all these filters, the only thing which comes through is a beam of neutrinos with some admixture of these sterile neutrinos. And then these sterile neutrinos in this big detector, it's like 50 meters long, can decay. So you have empty space, nothing happens, there is a vacuum there, so neutrinos just fly through, and sterile neutrinos decay. And there are 10 to the 20 protons which can hit this target over the course of several years. So you will create enough of sterile neutrinos that some of them will decay and produce observable signatures here. That's one of the types of experiments which can be done. Essentially, anywhere you can produce a beam of a lot of highly energetic neutrinos, you can produce some admixture of sterile neutrinos. And then you need to put some detector along the way, which will distinguish, which will catch their decays. Hope I answered the question. Now, another question. So 3+1 Seesaw models, 3+2 Seesaw models. The nomenclature here is a little bit different. What you probably have in mind is a story about sterile neutrinos, which I didn't discuss. It also exists, and it's related to some other experimental results, which have not yet been established. So we don't know whether it's experimental anomaly, some fluctuations, some experimental misdesign, or it's a real new physical signal, which would very, very strongly change my talk if this would be a confirmed signal, but we don't know yet. And in this model, there are not 3 mass states which are measured, but actually 4 mass states, or maybe even 5. And you try to bring this data together with what you know before, and it doesn't work, at least not naively, so something needs to be changed there. So the sterile neutrinos which I talked to you about, they have 2 or 3 particles, because you observe at least two mass splittings of your active neutrinos, these ones, the gray ones. So 2 splittings of active neutrinos mean at least 2 mass differences should be non-zero. That's why there should be at least 2 sterile neutrinos. Situation may be different, in which case more sterile neutrinos will be needed. I hope that answers the question without going into much details. If not, you're welcome to ask again. Now the question is whether it's possible to get away with nothing but neutrinos. No, the fact that neutrinos oscillate means that some particles should exist. Like what I showed you is one possibility. There are other very different possibilities, many of them, but something should exist. It may be very heavy particles or light particles or medium state particles, but something should exist. You cannot get away with just neutrinos. Moreover, even if it would be possible in the neutrino sector, you would not be able to deal with neither matter-antimatter asymmetry of the universe, why we exist, nor with dark matter problem, okay? You would still need some new particles. If you really want to explain what's behind these things. That would be my answer. There's a rule of conformal cyclic cosmology as it indicates repeating universe cycles kind of disproves the possibility of a big singularity. That's very far from what we're discussing. Now, I'm not a big expert in the conformal cyclic cosmology, and I don't think I'm qualified to say anything here. But what I want to explain to you, the current picture of the universe, which is presented here, tells you that there is something unknown which triggers an event of accelerated expansion of the universe called inflation. This accelerated expansion of the universe, we need it because without it, our cosmic microwave background sky would only be coherent on a scale of about 1 degree rather than 4 pi radians. So the fact that it's so uniform, that this v equals 10 to the minus 5, this fact kind of boils down to the question, as we believe, that somewhere very, very far in the past, there was this period called inflation. Has there been a universe before inflation? Yes, it may be. But the problem with it is that you need to produce an observational evidence or observational test of this scenario. Something which is not explained in the model of inflation should be explained in this conformal cyclic cosmology. Otherwise, your theory becomes untestable, which is still interesting philosophic exercise of the mind, but it's very different from a physics which we're discussing here, which is kind of phenomenology driven. I know that this cyclic cosmology, at least people try to search certain predictions of it in the cosmic microwave background data. I'm not an expert in it, and I cannot comment. Was it successful? Was it not successful? Was it below sensitivity? So you would have to look at this. I cannot say more. Good question. Can primordial singularity be responsible for matter-antimatter symmetry of the universe? Yes. Now, but the story goes in the following way. This period called inflation took a universe which was of a certain size and expanded it to the exponent to the power of 60, e to the power of 60, by enormous amount of times. So whatever was there at the beginning, whatever baryon number was there, was multiplied by e to the minus 60. And the observable number, which we are talking about, is about 10 to the minus 10. So whatever was hidden in the initial condition of the universe, pre-inflation, was diluted by extreme amount. Okay. Now, there is a process when the universe exits inflation. So inflation is not eternal. It runs for some time and then stops. And that's actually when hot Big Bang happens, because inflation is extremely cold. Your universe is devoid of matter, has no temperature to begin with, and then it kind of populates itself with a thermal bus of particles. That's called reheating. It is possible to invent a mechanism when matter-antimatter symmetry of the universe gets generated during the reheating. As I told you, what I'm presenting to you is one of the models. It's possible that it's not the correct model, and other models exist and can be correct ones. Okay, but it's a good idea. Young-Mills mass gap. Look, it's a completely different story. Now, how could it be helped? I'm not sure how much I can tell you here. No, not because it would take us very far afield. Okay, let me try to formulate it the following way. we can well explain the phenomena which are close to almost free system. If a system moves freely and then you kind of deviate it a little bit and it oscillates a little bit around its equilibrium position, you can describe it and do it with precision, do it with details, etc. Now, however, if the system is very, very strongly interacting, meaning that everything interacts with everything, your possibility to describe it is very limited because nonlinear systems, as you might have heard, are not well explained by conventional mathematical methods, apart from kind of direct brute force computations. The problem of the Young-Mills gap is one of such problems. It's a strongly interacting system. And there are a lot of ingenious attempts to try to test, to break it, to solve it. I think sooner or later it will be done. But it's very difficult to say what it will give you apart from satisfaction. I mean, there's no mystery which sits there, which you cannot explain. Sometimes you don't know what it is. Sometimes you don't know how to put an exact mathematical description behind what you measure. This is of a second nature. Why is there a particular reason why elementary particles have two types of chirality? Does quantum theory explain this? Yes, there is. More or less, it boils down to the fact that our space is four-dimensional and that our fundamental particles are fermions, have spin 1/2. These two stories tell you that every particle spin 1/2 should have two chiralities at a very simplistic level. So it's the special relativity plus quantum mechanics plus the fact that this is a four-dimensional space. In a five-dimensional space, if we would live in a five-dimensional space, this would not be the case. We would not have any chirality. Or in a three-dimensional space. Some other phenomena would exist there, but not this. Okay. So at some very philosophically fundamental level, just the fact that we are in 3+1, in three spaces in one temporal dimension. Now about the Young-Mills gap, this I think I already answered. Okay, colleagues. If you have any other questions, I'm happy to stay if you allow. If not,
yeah, that's fine. I will hand over quickly to our president of the Maxwell Society just to give some information about the social events happening tonight and tomorrow. But yes, you're more than welcome to stick around for a bit longer afterwards and answer any questions. I think we've got another one come up just now.
Yes.
But I'll pass over to Naira quickly first and then I'll let you continue.
Okay, very good. Okay, so Naira, you're talking now, right?
Hi, sorry, I think I was just getting the host permissions and stuff. Okay, yeah, so I just wanted to say, do come along to our talk tomorrow by, I talk tomorrow by Radin Dardashti about how scientific problems shape theory development. So he's actually a philosopher and he's going to be talking about philosophy and physics and how you can apply that to particle physics. And that's the last talk of our conference, so do come along to that. And also today we have a games night at 6 p.m. So the link to that is also going to be sent to your email. So do come along to that as well. And we're just going to be playing some games together. So yeah, I'll let you continue now.
Thanks. Okay, so the question about neutron star cores, could we place a satellite next to a neutron star and detect neutrinos or their absence? Yes, but keep in mind that the closest star to us is 4 light years away and it's not a neutron star. The distances there are completely impossible. If the neutron star would be at our backyard, God forbid, because that's not the nicest neighbor, it would be extremely difficult to create a satellite which can withstand environment of a neutron star. But yes, many things can be learned about neutrino physics. If, for example, a supernova will blow up tomorrow, I mean, if it will blow up too close, we will all die. but if it will blow up reasonably far away, like Betelgeuse or other stuff like that, our telescopes will get a lot of neutrino signal, and we will learn a lot of stuff, including probably the presence of sterile neutrinos, which can be emitted out of the stars as well. So no, we cannot put a satellite next to the star, but yes, we can put a telescope looking at a neutrino emitting object like supernova. Because when neutron star neutron stars is born in a supernova explosion. And that's this event which takes place. This is called proto-neutron star, where neutrinos fly out. And that's what we very much hope to see, because some of the stars we know about are ready to become supernova any day. What laboratories are working to detect sterile neutrinos? Well, CERN, first of all. And at CERN, there are several experiments, like not one, not two. Like, let me show you. So the Large Hadron Collider itself searches for it. Now, this, and these are proposed experiments. This one is not only proposed, but even approved. It's a fun experiment when there is a Large Hadron Collider. It sits in a circle. And neutrinos, if they would be created, they fly tangentially to the circle. They just go through the Earth, through rock. And there is an abandoned tunnel from some previous experiment where you can put your new detector called phaser, and it will detect neutrinos or sterile neutrinos of some kind, of certain kind, and other things. There is also an experiment called NA62, which also works there in search for sterile neutrino. Another type of laboratory which does it is Fermilab in the United States. They're planning a big experiment called DUNE. It's mostly devoted to neutrino physics, but can also do this sterile neutrino physics. Some kinds of neutrinos can be searched by IceCube, this big South Pole laboratory neutrino telescope. Japanese experiments, G2K, Super K, Hyper K, also search and plan search for this. Essentially, today, any big laboratory which works with neutrino physics does some search for sterile neutrinos, plus Large Hadron Collider. Do neutrinos form inside protons? No. Neutrinos do not participate in strong interactions. That's why gluons and neutrinos do not interact with each other. Let me jump here. Sorry. Just a second. Yes. So these are particles which participate in strong interactions. This purple quarks and this gluons. And neutrinos are not part of this. Neutrinos participate in weak interactions. And yes, particles can participate. Protons contains quarks, and quarks participate in weak interactions. This is how neutrinos are created, for example, at Large Hadron Collider, but not inside nucleus. There it's a different condition, and there's nothing there which produces neutrinos. Inside, accidentally inside, not inside protons, but yes, inside nucleus, of course, they are produced through beta decay. Will you have access to my slides? No problem. If there is a place for you to host it, then I'm happy to provide them. If not, I can put them on some website of my own and send the links to you. So any way is fine.
Brill, I think that's all the questions. Yes, and with regards to the slides, I'm happy for you to send them to me, and then we can send out a general email. That's what we've been doing with the rest of our speakers. Thank you again so much, Oleg, for sticking around this long. I think you provided your email at the beginning of the slides. Yes. So I'm sure if there are any more questions, then people can email you directly.
Yes, exactly. You are welcome to email me. And yes, thank you for the questions. They were extremely good. I really enjoyed, given that you are at a very young level. I'm happy to see so many people with such interesting physics and questions
Yeah,
which are quite non-trivial to answer, I must say.
it was very engaging. Thank you so much. And unless we have any more questions, I'm going to end the meeting here. Thank you again so much, Oleg.
Yes. Thank you.
And hope to see you all tomorrow. Thank you very much. Goodbye.
Bye-bye.